Last we talked, we were exploring epsilon soft. I can turn off this annoying bar ahead of. This too. So, since we are all prepared for this exam, and epsilon soft is on this exam, who can recap the concept of epsilon soft for me? What is this doing in a Monte Carlo environment?
It's implementing exploration as part of the actual
The policy itself. Yeah,
Haha, I remember
yeah, that's
something.
exactly right. So exploration can be done in a couple of different ways. You can either build exploration into just the start, where we're going to randomize where we start, or you can build exploration into the policy that says, now, even if I have learned what I think the optimal move is, with some probability, I'm going to take a random action. And that random action will get a larger sample size for all of these actions that may be suboptimal, may seem suboptimal, but with a larger sample size may become optimal. And that's what we need in order to be able to prove that this policy is optimal.
There's a lot of people that didn't show up for their meeting exam today.
Let's see, that's
Pretty full to me.
There's not a lot of people.
Yeah, 19 out of 24, it's kind of a problem. We'll see if they show up. Maybe they're just delayed a little bit. So that's the concept of epsilon soft, and as we move past this, we can look at the pseudocode for epsilon soft. Really, we're just selecting whenever we select an action. This is just the general Monte Carlo process. Whenever we select an action, we're going to decide now, we're gonna roll an RNG between 0 and 1. If the number is above epsilon, then we're going to exploit, and if the number is less than epsilon, then we will explore. So, is that right? Epsilon was the exploration rate, I believe. So with 1 minus epsilon, we're exploiting, with epsilon, we're exploring. So that's exactly what you want to do. Generate a number between 0 and 1. If it's above that parameter, then we exploit. If it's below that, then we explore. Let's talk about what this means in terms of policy and agent action decisions. This for me, when I first learned reinforcement learning, this is one of the sticking points that took me a couple of years to really fully understand it intuitively. So I'm hoping that I can explain it in a way where it does not take you a couple of years to get it either, because that was not so fun. But the basic idea of on policy and off policy is exploration built into the policy, or are we keeping track of two separate policies, one of which is what we want to do, and one of which is what we are doing? We will apply the what we are doing algorithm in order to train what we want to do. Which kind of seems really strange, but it's the concept of, I want to, in the future, know what the best decisions are for myself. So I'm going to take actions that I know are suboptimal with the purpose of learning what is optimal. I know what I'm doing is a mistake, according to the knowledge that I've gathered throughout my life. But I'm going to purposefully make that so that I can learn from it. That is the behavior policy. The policy that we actually use for taking actions. And then we're evaluating a different policy that we use, that we're keeping track of what are the actual best actions to take. So we make the mistakes, we learn from the mistakes, and we get a model, a combined model that we're using that is the optimal policy that we're generating. What actions should I be taking based on the actions that I'm actually taking that involve exploration and making mistakes? So on policy, built into the policy itself. The policy that we follow, we will be making those mistakes, and we will be analyzing things based on those mistakes. Rather than building a model, so we're trying to build a model here that incorporates the mistakes such that we have to make an infinite number of mistakes, but we still want to optimize the policy. In off policy, we're separating those two into two separate policies, a policy we follow and a policy that we are learning. Does that at least start to make sense? We'll see what that's like with applications here in a second. Because we will see how different algorithms prioritize and handle the on policy versus off policy discussion. But to actually evaluate an off policy, we now need to decide and find how to update a policy that we aren't following. So again, the behavior policy is what we are actually doing. And the target policy is what we are learning. So a behavior policy can look more random because it's going to be doing lots of exploring. When we do that exploring, we'll be building an internal model that is not what we're using to make decisions, but once we decide if we wanted to suddenly go from training to performing optimally, we would now apply the performing optimally algorithm. So this trains and this performs. As we train, we explore everything infinitely because we're making mistakes. And as soon as we need to kick into high gear and perform, we switch from using this policy to using this policy. To do this, we need to come up with the relative ratio of how likely it is to take a particular action between these two policies. What is that ratio? So for instance, it's not possible to move left with this target policy. But it is possible to move left with this policy. So that ratio is either 0 or infinite, depending on which is the numerator or which is the denominator. The likelihood of going up, on the other hand, also is likely to not be exactly the same. Each one of these is going to have an associated distribution. You can imagine this as something like, which of these has juice? We're feeling orange today. The behavior policy would state that the probability of, let's say, up, the probability of left, the probability of right. You know, this has to be a function, so this has to total a probability distribution. This has to total 1. So maybe this is a random policy. So this is 1/3, 1/3, and 1/3. And then the target policy says that, well, left is just garbage. We want to get to green, and we found that really the only reasonable ways to do this are to go right and to go up. Because if you go left, you kind of have to work your way either back or go all the way around. Even if you go right, maybe it performs well enough that it's at least worth considering and taking into account. So we would have something like the target policy is going to say that the probability of going up is 0.9, and the probability of going right is 0.1. We can now come up with the associated ratio between these values for probability of up and probability of up. That would give us a ratio. How likely are we to take that move in this policy compared to this policy? Yes, no, makes sense? We call this concept importance sampling. So we're going to see a slide with a disgusting amount of math, but that's really all this is saying. Is saying that these possible, not just decisions that you make, but now certain trajectories. How likely is it, given that we are here, if we move up, that we end up going up, up, right? That is a trajectory. We're looking multiple moves into the future. If we move right, how likely is it to go right, left, up, right, to be able to get to the target destination? So we're going to come up with the ratio of probability given the two different policies. So this is the target policy and this is the behavior policy. So target policy is the numerator, behavior policy is the denominator. And we're going to say for every step in this trajectory, which is why we take the product. So if we've seen, I'm sure, hopefully we've seen this notation before. Capital Pi is just the product of how likely this is given a particular policy. So this would be saying something like, we care about the probability in this policy of going here, here, there. Policy here, going here, here, there. What is the associated ratio of these trajectories given these two different policies? That is the importance sampling ratio for that trajectory. And you would see that the way you would calculate this is the probability that given that we're here, we move here, given times the probability that given that we're here, we move here, times the probability given that we're here, we move here. Since those are dependent events, you have to multiply them. Same thing here. But since these are different probabilities, you'll get a different probability of taking this entire trajectory. So that is the concept of importance sampling. The idea now is that the return that we get from this, when we're looking into the future, saying how good is it to be where we are, we now need to weight this, how good is it to be where we are, based on the difference between, since we've only ever explored this world according to the behavior policy. We've never implemented this policy before. This is a policy that we're learning behind the scenes. Imagine this is like, let's go with a ridiculous example. I've gone on 100 dates in the last year, and intuitively, I know that the worst thing to say as an opening line on a date is, "Hi, I am the coolest person you've ever met before." And yet, whenever I'm on one of these dates, I can't help myself. With some probability, I say that, and it immediately ends the date because obviously I'm so full of myself that no one is interested in that. So I would be learning and analyzing about myself, saying, I should never do that. That's just not something that's good for me to do. But with the behavior, what actually happens, with some probability, I actually do that. With enough evidence, I would be able to say, okay, I should stop doing that. It's never worked. So maybe I should learn from that. But according to the behavior policy, I'm always exploring. Maybe it will work the next time, even though the last 100 times it hasn't. You can see how there's a difference between what we want to be doing, what we're learning to do, that is the optimal thing to do, and what we are actually doing, which is suboptimal. That said, maybe you've just gotten unlucky these first 100 times. The law of large numbers will kick in after 1,000 times, and we'll show that that's really the best opening line to say. We wouldn't be able to prove that for sure without getting more and more and more samples of it. So that's what's being shown by this associated ratio. How likely are we to end up in a particular trajectory, given that we use the target policy, the policy that we're learning, compared to the policy that we're actually using to make decisions. So this is only in an off policy environment. We're not talking about on policy at all here. This is when we have two distinct policies, one that we're adhering to and one that we are learning is what's optimal to do. Does that make sense? Questions on that? There's one more important idea. I think I've asked this in here before, but remind me, raise your hand if you've taken a machine learning class before. The grad students +1. Perfect. So those who have taken machine learning, do you remember the bias variance trade-off?
Kind of.
That's something that is very frequently discussed in a machine learning situation, but let's actually look at kind of this trade-off that we have to make when we are learning. So bias is any kind of assumption we make where the difficulty of learning gets reduced, but the accuracy also gets reduced. So let's say life is complicated. I want to learn what the best opening line is on a date. If that's a complicated question. It depends on a lot of different variables. I could make a simplifying assumption that everyone I could possibly go on a date with has exactly the same personality. That is a simplifying assumption. It would make analyzing the problem simpler. On the other hand, it would make it less accurate because obviously people have different personalities. So that would be a type of bias, a simplifying assumption you make so that you can learn something faster. It takes something that would take 1,000 years to learn, and now it takes less time to learn than that. But because you made that simplifying assumption, it's not quite as accurate as it otherwise could have been. Variance, on the other hand, if we use different training data, how much does what we learn change? So imagine now the training data that I use for going on dates is a bunch of West Coast people versus East Coast people. how would how I learn how to hold myself differ if I were dating West Coast people versus dating East Coast people? Very different culture. What works in one isn't necessarily going to work in the other. So if we use different training data, if I'm learning how to hold myself in these situations based on differences in culture, then what I'm going to learn is different. So that's the concept of variance. So simplifying assumptions versus the training data that I use to make my function of how I should behave. Do note, though, that these are actually inverses of each other. As bias increases, variance decreases. As bias decreases, variance increases. You can't hit a world where there is no bias and no variance. You have to make some, if you use one or the other in different amounts in order to simplify it enough for this result to be calculable. That's how I would state that. So in order to make this problem solvable, we need to reduce the complexity somehow, and that's going to be either introducing bias or introducing variance. No matter what we do, this concept of irreducible error is something that you just can't account for. You can't train for. Unknown variables that influence the mapping of input to output, it's not something that you're considering. So for instance, let's say I'm trying to build a model of how to be successful on a first date. And I think that there are 6 useful characteristics, and I list what those 6 useful characteristics are. They're from the wording that I use to the conversations that I decide, but there's one big thing that's missing from this that I don't consider: personal hygiene. That would be irreducible error. Something that no matter what I do with these 6 variables that I'm trying to consider, there is this 7th variable that's really important that I'm just not considering. No matter if I optimize these 6, I'm still gonna fail that 7th one that I'm not thinking about because it's not something that I'm prioritizing. So that's the concept of irreducible error. So the chosen framing of the problem: what inputs are we using to try to learn the target output? If we're not using the correct subset or the most important subset, then we end up with error that we can't account for because we're not framing it in the problem. I don't care how exciting of a person you happen to be. If you haven't showered in 2 weeks, we're probably not going on a second date. So with that as background, let's talk about what we call ordinary importance sampling. So ordinary importance sampling is importance sampling that we guarantee there is no bias. We're making no simplifying assumptions whatsoever. But the distinction of how we are learning based on the training set, that was the variance, is there's no limit to that. We have different experiences, we're going to learn completely different target functions. So this tells us exactly how to do that. We're going to sum for all time steps. Remember that this symbol was defined back in the regular. Before this. Row that was done there. We're going to define it here. Where was that defined? It was defined somewhere, but I forget where it was.
Is it defined in the future?
That's always a useful guess with math, but I don't think so.
I tried.
It's the size of your sample. That's the size of your number of states. That has to be the case. So for each time step in the run, we'll go with that. I think that has to be. So it's the trajectory. It is the trajectory that we used. So not my final answer because that's this. This is the trajectory that's defined. It's the ratio that's defined by this particular trajectory, but it doesn't show up anywhere in the associated trajectory. And I forget what that represents. So we have a function, but I can't define what that function is, which is really unfortunate. Luckily, that's okay because we expand it to be more complicated on this slide. So let's actually go through, and this one we can use. I think it's a simplifying version of all of this. I think it's a new symbol that is implemented to simplify this process. So with importance sampling, with no bias, how do we come up with a Monte Carlo run with particular trajectories where we can learn what the difference is between the probabilities of those trajectories in between a behavior policy and a target policy? So remember that this is the importance sampling ratio right here. So we've already calculated that, but if you want to come up with what we call an ordinary importance sampling, we're trying to define the value of being in a particular state according to a particular policy. So we're going to declare that that is equivalent to the expected value of that policy, given the return at time t, given that we're in state S at time t. So that sets the stage. This is kind of the setting of a novel, if you will. We're in a particular state in the middle of this Monte Carlo run. So you can think of this like you can take any game that we want. If we choose chess, think of it as just in chess notation, we have just, move 1, move 2, move 3, and we're just defining the game in chess notation. We would want to be able to say, what is the expected value according to following a particular policy for being at this position? So here's the history. We know that with this history, we could draw a chessboard and we could give a snapshot of the game as it currently exists. How good is it to be in this state? We answered that question in dynamic programming with Bellman, but that relied on having a full sweep of that state space, or being able to know what all of the states are, what all of the associated transition probabilities are, how likely is it we end up in each successive state. In Monte Carlo, we don't know that. We're trying to learn from the experience itself without being able to zoom out and analyze all possible moves. We just have to use our own experience to do this. So how good is it to be here? The expected value of this is just the return that we expect from being here, given that we are in this state. So that is really just the definition of the value of the state, right? How likely is it that we win the game from here? That's really all that's stating. If we wanted to define what that means, if we're using an off-policy algorithm, then we want to sum the product of from K is the kth action that we take in the kth state that we visit, from K equals T, the current time step, up to the time, the step before we terminate the episode. So maybe eventually down here we lose. So this is at time t. Time t minus 1 is the time step before the opponent beat us. So this would say we're going to multiply the trajectory of how likely is it for everything that we could take to go from here to there. So that's the product. This becomes the trajectory. According to the policy, when we're in this state, what actions can we take given that we're in that state? So we're going to go through every possible action and we're going to say, what is the probability that we end up in the next state given that we started in this state and took that action? So there's a massive branch here. There are a ton of possible different actions that we could take from time step 3 to end up in time step 4. Based on our own history, we have come up with an associated probability that is embedded in our policy. Our policy tells us how likely we are to take each of these actions. If we're using something like exploring starts, exploration was built in here. If we're using epsilon soft, we have an idea of what the optimal action is, but we are not doing that. In this case, we are saying we are going to explore in a real policy and learn a target policy that is the optimal policy eventually. Lots of different actions we can take here. So we're going to come up with the associated probability of getting to the next state given that we are in this state. And do note that these arrows go to different possible states. So this isn't all just going to 4. This is going to, knight to this position, rook to this position, queen to this position, etc. All different states for all the different actions we could take from here, the associated probability times the return from there on to the end. So all of the possible trajectories that we could take. So we need to sum up all of those trajectories and the associated probabilities for those trajectories, given that we're in this state, which is kind of gross. You can see how this is really bad, even for something as like chess. How many trajectories are there from a particular position?
Yes.
That's the correct answer. There are lots of them. In a simpler environment, you would have fewer of these and be able to learn them faster. But you're going to sum up all of the possible trajectories through that. This tells us, though, that since we are using a behavior policy and a target policy, this is based on the target policy. Keep in mind that this is using the target policy. So we're analyzing this not based on what we've done, but what we have optimized. I've done a bunch of stupid stuff, but I've learned from it. And now I know how to hold myself and handle myself a little bit better. So I'm going to use what I've learned as I analyze the state space. And then what do I do after I've done all of that analysis? Back to my old self. I'm going to make some mistakes. I'm going to go use the behavior policy again. And I'm just going to continue updating the difference between how I think it's optimal to act and then how I act. But only by making those mistakes can we really optimize and know for sure that I now know how to hold myself the best that I can, because I've made those mistakes over and over and over again. Does that make sense? So this difference between what we've done historically and what we want to do is based on the importance sampling ratio. So this just becomes a coefficient to this process. This breaks down into exactly what we've done before, but we're going to swap out the target policy for the behavior policy. We just need to use the ratio between how likely each of these trajectories are according to those two policies, because what we really want to update is the behavior policy. Sorry, we want to update the target policy and we don't want the behavior policy to change. We're going to continue to do this, but we need to learn something about this, because what we are seeing is this. So we need to convert the target policy's optimization into how likely is it that the behavior policy generates that trajectory. That allows us to now phrase this same question. What is the expected value according to the target policy in terms of what is the expected value in terms of the behavior policy? So this is just finding a way to convert between how likely is a trajectory, how good is it to be in the state according to one policy, how good is it to be in the state in terms of the other policy. It's just converting between those two, which becomes really important if you want to learn from your experience. You do something that's stupid, you don't just want to learn how you're going to act based on that. You want two separate policies, what I do and what I think I want to do. How are we doing? Does that make sense? Somewhat?
At the moment.
Until you prod it a little deeper, yeah. That's funny.
Don't ask me tomorrow, I won't remember.
Yeah.
Oh, I'm just a little bit confused about the conversion between what we believe to be the optimal policy versus the actual policy we're gonna use while playing.
Yeah. Yeah, so this is the behavior, so this is the training behavior and this is the performance behavior. As we get experience, because we need to know that what we're doing is optimal, we are going to convert between the two. And the only thing that is different here, you can see that the policy is different, but this is the same, this is the same, same. It's literally the same. The only thing that is different is this coefficient that is the importance sampling ratio. That is the probability that a trajectory is visited between the two. So what we will eventually want to do is update the target policy and how likely we want the target policy to be taking that action in this state. given the behavior policy and how likely it was. So we have to analyze what is the expected value of being in this state according to those two different. It's easier to see as you're right close to winning. Let's say right here, there is an action where we could either lose or we can win. It's a very fickle state at the very end of chess. One move, we checkmate them. If we don't make that move, one move, they checkmate us. The behavior policy is not going to be optimal. With some probability, it's going to take a random action. If there's only one action that wins the game and any other action will lose the game on the following play, then the probability of winning, according to this behavior policy, is not 1. But according to the target policy, since we can win with a single step, we should be doing that. We should win. But it won't get us additional information about how to perform, or that that is for sure the optimal action. We know that it is, analyzing it as humans, but as a machine, we don't know that for sure. So we need to incorporate some exploration into that. How do we convert between how good is it to be right here according to this policy? So let's say if we lose, we get -1. If we win, we get 1. According to the target policy, what we eventually learn, the value of this state is our discount rate times the fact that we're always going to win. So the target policy is going to think that this state at time t-1 is really good. On the other hand, our behavior policy is going to do something random. If we do something random or with some probability we're exploring, then this value is lower than that. So we can figure out the difference between the probability of winning the game according to the target policy and the probability of winning the game according to this behavior policy that's still exploring. And that ratio would be the difference between the expected values of those two different policies, given that we're in this state. Does that help or does that make it worse? Didn't hear it helps.
I think I understand it at that moment.
Ignore the math, exactly, a lot of these symbols. If you get understanding and the intuition of just we care about converting the expected value between the expected values of these two policies, given that we're in a particular state. That one policy we're designing to be optimal, and one policy we're designing to be able to prove that this is optimal. That helps. There's no way to know that this is optimal unless we keep making mistakes. We have to explore suboptimal moves an infinite number of times in order to prove that this is optimal. Once we stop training, we want to stop doing this. We want to start doing this, because this is where we want to, this is the performance algorithm.
So essentially, one is mapping out the whole space, and the other one's like, okay, with this map, this is the best path.
Yeah.
Okay.
Yeah, this is saying that we can do a bunch of things. How do we know that this is the best thing? Because we've tried a bunch of things that weren't that. A lot of times. And then the law of large numbers kicks in and we actually get more and more and more evidence that this is the best way to handle it. Or if it wasn't, then this explores to the point where we find that this was suboptimal, so we can update this based on the information that we're gathering from this. This is the information gatherer, and this is the information optimizer.
So knows where it is by calculating from where it isn't from where it's supposed to be. Then
Yeah.
it lives where it's supposed to be, where it isn't, where it's not currently, it knows where it is.
That's an interesting way to think about it, but it's not completely wrong. So this is again a zero bias solution to this. So we're not making any simplifying assumptions. Yeah, no simplifying assumptions being made. But different training data, we take very different trajectories through the game of chess. What we will learn is optimal, completely different. There's unbounded variance. There's no guarantees that learning this from scratch 2 different times doesn't produce wildly different results. We get we can't draw any conclusions about how well this converges over the long term. Think of it like, maybe I can give people who play Magic the Gathering a little bit of an idea. So I've talked about it before in the prior class, but Robo Rosewater, the AI that generates Magic the Gathering cards, you can imagine that you're starting training it from scratch. Something that has zero bias would say, we are taking into account every card that has ever been printed in Magic the Gathering, regardless of how old or outdated some of the wording is. We're not making any simplifying assumptions about the state of Magic the Gathering.
Gave us confetti.
On the other hand, we train that agent for, let's say we trained it for 100 years. And at the end of that, we want to see what kinds of cards it generates. There is no guarantee that these two different trained 100-year algorithms produce anything similar to each other. They might, but they might not. There's no theoretical guarantee about how similar the results of that is going to be. Unbounded variance. But we didn't make any simplifying assumptions. The more we simplify Magic the Gathering down into fewer and fewer rules, fewer and fewer allowable possible wordings, the more that variance starts to become, these agents are going to start to perform the same after it finishes training, that it generates very similar kinds of cards to each other because we simplified the search space so much. What does it look like on the other hand? Yeah, I guess this is further proof that it gives you unbounded variance. Here's a very simple game. Let's call it a game. We start in this state with probability. If so, we have two actions that we are allowed. We can either move left or move right. If we move right, we immediately terminate the episode and get a reward of 0. And then we find ourselves in the next version of this world, back in the starting state. On the other hand, we can choose to move left. If we move left, 90% of the time, we get a reward of 0 and end up back in the starting state. It doesn't terminate the episode, but we find ourselves, we didn't do anything back there. On the other hand, 10% of the time, we get a reward of +1 and the episode terminates. Let's say we want to now figure out what the best way, the different ways that the two behaviors, the two different policies would work. So what is the probability of choosing left given that we're in this state? What is optimal to do? Trying to figure out how to optimize the return for this, it makes sense that the best thing that we can do is go left, right? If you go right, then we immediately get that reward of 0. There's no way to get that reward of 1. If we move left, there's no way to perform worse than a reward of 0. But there's a chance that we can get a reward of 1. And if we just choose left, 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 eventually we will terminate with a reward of +1. The behavior policy is going to say, well, we don't know, just because we've chosen right 5 times and gotten a reward of 0 each of those times, there's no guarantee that this isn't something that looks exactly like this, except a reward of +100 instead of +1. We don't know that because we can't see the environment. All we know is the sequence of actions that we've taken and the associated rewards that we got from taking those actions. So how do we show that? We have to be able to prove that left is better than right. We need a behavior policy that explores both of these infinitely. So what we're going to do is we're going to choose left versus right arbitrarily. So with probability 1/2, we're going to choose left. Probability 1/2, we're going to choose right. This will fully explore the space. And if the law of large numbers kicks in, after we've trained this for a very long time, we have 1 billion examples of moving right and never getting any reward. Is that proof that we will never get a reward? No, maybe the chance is 1 in a trillion that we get something really good moving right. But it is starting to get less and less likely that it is worth continuing to explore going to right. So we want to update this policy that says, according to the information that we've gathered so far from this policy, it looks like the best thing to do is always go left. As we continue exploring this, we update this to converge to this probability of 1. And as soon as we need to now it's for real, we're not trading anymore. We want to maximize the amount of return, the reward that we get, and you get 100 episodes of this. Whenever we hit the end, we're done. This is the policy you want to implement, because it's the optimal policy. It'll maximize the rewards that you get. But the only way we know that that is true is because we trained on this. If we wanted to come up with an equation to figure out what is that variance, how likely is it that when we train two different agents according to this, that they come up with different policies? There's no guarantee for this. And the reason for that is there is a reasonable probability that every time we explored left, we just got left, 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 right. And we terminated it with choosing to go right with that 1/2. We never got this left that gave us a +1. It is possible that happened. There is no guarantee, there's no amount of a sample such that we are guaranteed to have converged to this. Because there exists a non-zero probability that every time we've gone left, we haven't gotten a reward. No theoretical guarantee on that. Does that make sense? We're just looking at theoretical guarantees here. You do this long enough, it is very, 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 very likely that you've learned that left is better than right. But there's no guarantee. Because there is a probability greater than 0 that you've never seen it. So that's really all this is going to go through and show us, is that the actual estimated variance of this is infinite. If you apply the variance estimator from this expression here, we find that it is infinite. But I think rather than go through that, just having that intuition of there is a non-zero probability helps with that better. You can also see what this looks like in practice as this trains. Because we're using a learning rate of some kind, even late in episodes, you can find that suddenly agents decide that the estimate of the value spikes. It doesn't really converge. There's still variance, no matter how far into the future you look. So it never really converges. All right. You can also see that they're very different, even at different points in time. Even if the estimate here between 9 of them is within, there's the 10th one that is very different from it at any particular point in time. Weighted importance sampling just says now we're going to parameterize this to now has bias that we start to make those simplifying assumptions as we find that unbounded variance. We start to make those simplifying assumptions until we converge on agents that learn the same thing. So preferred because it has lower variance, it doesn't have unbounded variance, it has a guarantee of some variance. So I don't find this to be the single most important thing that we cover. But if we use importance sampling and go back to blackjack, here is the error associated with how the average over 100 runs of how much error there is in terms of the associated where should you hit and stick. The error, if we use ordinary importance sampling, converges pretty quickly after, this is a log scale, some number of episodes. And with weighted importance sampling, it actually starts out quite low and you learn significantly faster. So it's usually what you want to use. Especially if you don't have time to train over long trajectories, something like the game of chess. All right, incremental Monte Carlo. Instead of first visit, remember that first visit was the idea of we can get back to a state that we've been in before. Think of this as like chess. I make a move, my opponent makes a move, I make that same move in reverse, my opponent makes that same move in reverse. We don't want to necessarily consider the fact that via some discount factor that we got back to where we were before. We're going to use just the first visit. We're not going to update this again based on the fact that we're in a state that we've been in before. So we don't necessarily have to track all returns in an incremental Monte Carlo. We use ordinary importance sampling, or we can use weighted importance sampling, and it changes just how we come up with the value of everything. So this really dictates This is the same Monte Carlo algorithm that we saw before. But now, for each step of the episode, we're using the ordinary or weighted importance sampling here in order to converge faster. So we don't need quite as many iterations with this to converge. This is all just theoretical, will converge faster, and in practice it does. Again, not the most important thing that we've covered so far, but useful nonetheless. Right, next, we've kind of talked about this. So this leads us to the off-policy Monte Carlo algorithm. The full off-policy Monte Carlo control algorithm basically says we still have those two policies, the target policy, the behavior policy. We're looking at single runs, single trajectories from a starting state or a current state through all of the possible trajectory down to a final state. And then we can backtrack all of that. And then we can use the expectation maximization algorithm that we did through general policy iteration that we showed at the end of dynamic programming, where we start with a random policy, we evaluate that policy via Monte Carlo, via importance sampling, and an off policy coming up with the difference between how likely is it that we see this trajectory between the target policy and the behavior policy. We can use that to update the policy. As we see here, we're looping forever, we're generating episodes for each of those, and then we update our policy. You see that the policy here just becomes a greedy, what is the best action that we can take from here, which is exactly what we found in dynamic programming as well. And from there, we improve, and we evaluate, improve, evaluate, improve, evaluate, improve, until our value function and our policy converge on the optimal policy. So our target policy is constantly changing based on the experience that we're getting from our behavior policy until it is optimal. So we use that exact same algorithm to converge this as we did to converge dynamic programming. How are we doing? Does that make sense for Monte Carlo? Really, those are the three main ideas. Three main ideas, two policies, trajectories, importance sampling between them. Learn based on this so that we can update this. Do that back and forth like this. Evaluate, improve, and that is shown to provide the optimal policy. After enough time. For complicated state spaces, this can still take a very, very, very long time. Which is why we can't use something like this to immediately solve chess. But we can use something like this to immediately solve tic-tac-toe, because it's simple. There's the algorithm. Summary of Monte Carlo. Learns from experience instead of an abstract view of the problem domain. You learn by directly interacting with the model. You're learning from playing the game and not from thinking about playing the game. In dynamic programming, you can learn offline. You don't have to be playing the game. You can think of, since I have a full view of every state and action that I can take, I don't have to actively be playing the game. I just use math and learn from math what to do. Think of it like sitting down and thinking about playing the game instead of playing the game. In Monte Carlo, we can't sit and think about the game because we don't know all of the associated probabilities for the full state space. So we have to sit there and play the game. You sit down and play a board game that you've never played before. You read the rules so you know how to play the game, but you haven't developed any reasonable strategy yet. You can't sit down and think about what is the probability in Catan if I choose this particular starting position. How likely is it that this is the right decision? You don't know that until you've actually done it, experienced it, and have some experience to determine whether that is a good initial move or not. We need to maintain exploration so that we can show that the policy that we generate eventually via this generalized policy iteration is an optimal policy. If we don't explore, then there is significant bias in that process we're using our experience in a limited sample and making large sweeping conclusions based on that limited sample size. If we explore forever, then if there is a better policy, we will find it. The concept of off policy, we're separating two policies. So instead of incorporating the exploration into the policy, what we're doing and what we're thinking about are two separate things. What I think and what I do are distinct. For importance sampling, we had two different forms of importance sampling. Weighted importance sampling converged faster than ordinary importance sampling. So this is the second of three major reinforcement learning domains of algorithms. The first was dynamic programming, the first was Monte Carlo, and the second is third. The third is temporal difference.
So the first twice.
Yeah, that's why I wanted to say the second. The first, the second, and the third. I haven't had coffee. My office hours were busy. I need coffee.
Oh, sure, you're just blaming students.
Not the students' fault for using office hours. So dynamic programming, we had this full view of the world. So we could say, what is the value of this? It's based on what we've calculated as the value of these. What is the value of this? Well, that's based on everywhere we can get to from there. Value of this, everywhere we can get to from there. So we can analyze the entire search space. With Monte Carlo, we don't know what the search space is. We just know when we are here, here are our possibilities. So we're going to, according to our behavior policy, we're going to make some decisions about where to go. As we do this, we're going to update how well we think this is according to the target policy that we're learning, because we have an additional sample of having taken this trajectory through the state space. So we can use that to backtrack the result of this back through the target policy without changing the behavior policy. How likely was it that the target policy would have taken this particular route? Maybe it really wanted to take this route, but the behavior policy said, I know you want to go here, but we're going to go here instead. So you backtrack that, and maybe this caused this to win the game. And the target policy goes, wait, what? I thought we always lost the game when we did this. So now the target policy has more to think about, more information about what happens when you go down this route, and maybe that changes what the target policy wants to do. Maybe this is the first time we've ever explored down this path. And now the fact that we won on the first try, the target policy says, wait, we were 1-1 when we went down here, but now we're 1-0 when we go down here. I'm going to change to where instead of going down here, I want to go down here. And the behavior policy will continue to explore this space, and the target policy will learn based on that experience when it becomes time to really perform, what should I be doing? Temporal difference, on the other hand, says why wait and simulate an entire episode to be able to say something about this starting state? We can use a combination of dynamic programming and Monte Carlo to now make a decision about where to go next based on this, but still utilize the experience of this to learn. So the temporal difference is a combination of dynamic programming and Monte Carlo in a way that, as we will see, is very interesting and allows us to learn some things differently and more interestingly than Monte Carlo. So we'll start by talking about one-step temporal difference prediction. So Monte Carlo waits until the episode terminates. We get no information about how good the current trajectory is until the end of the episode when we get a reward. We either won or we lost. Great, let's back propagate all of that through every decision I made in the entire episode. With temporal difference, we are going to now just wait until the next time step. At the next time step, we're going to use the expected value of being in this state to back propagate that, just that one step. So it looks similarly to the grid world example, except that we're using real trajectories now. Instead of sweeping over the entire state space and analyzing it, we're going to have a particular run through this that generates a trajectory. But instead of waiting for the episode to terminate, we're going to go one step. Say, according to the best estimate we have so far, what is the value of being here? Let's backtrack that to where we just came from and update that immediately. So we're not using the real value of the final result. We're using the estimate that we have for the value of that state. So one step TD prediction is not the best thing to do, but it creates an interesting alternative to Monte Carlo. Let me give you an example that will illustrate the difference between these two algorithms on something that might be a little bit more useful. So here is your commute. You leave the office, it's Friday at 6 o'clock. The steps that are involved in your commute is going from the office to your car, going from the car to the highway, going from the highway to the exit to the highway, and going from the exit to the highway to home. Those are kind of the distinct, discrete intervals that we're going to map the time of. How long does it take for me to do part 1, 2, 3, and 4 of this? Sometimes something happens in the middle of that, like you get stuck behind a truck. You get boxed in behind a truck. And because of this, it takes you a little bit longer. Think about estimating how long it's going to take you to get home, given you're at a particular state in this. So you're leaving the office, it's Friday at 6 o'clock. Your significant other calls and they say, how long until you get home? And you want to give them a realistic estimate of how long it's going to take you to get home. You would have a long history of leaving the office Friday at 6 and be able to say something like, I'm going to look at the average, and it's a 30-minute commute on an average Friday at 6. So the predicted total time that it will take to get there is 30 minutes. However, of course, your office, being you're a computer scientist, has like windows, you can't tell what the weather is outside Friday at 6. You go outside and suddenly it's a downpour. Because it is raining, you know that people are going to be driving a little bit slower, it's going to be a little bit more dangerous, so it's going to take you a little bit longer. So it took you 5 minutes to go from the office to your car, but you now think that it's going to take an additional 35 minutes from there because it is raining. So the predicted total time now is 40 minutes. But you're not waiting until you get home to be able to go back and update how long you think it's going to take the predicted time to go. You just wait until you reach the next step and you say, based on the current state, wait, the state has diverged from the average state from this point. So now I can update my significant other and say it'll be an additional 35 minutes before I get home. On the other hand, so if you get to your exit on the highway and it turns out that it only took 15 minutes from here. So elapsed time has now been 15 minutes. And you had anticipated that it was going to take 20 minutes given the raining, but maybe traffic was just a little bit lighter than you expected, and you saved 5 minutes on the highway. Great. Now you can update your significant other and say, I'll be home in 15 minutes instead of what I had estimated as 20 more minutes from here. So great. Then you get on, you take the exit and you get behind a truck. And now this is a 1-lane road and you have to follow a truck and you can't pass that truck from all the way from, I don't know, Cheney to, I don't know, the Cheney Spangle Road is one where it's hard to pass on, for instance. So you would get behind a truck and now you go, well, it's been 30 minutes and I think it's going to be another 10 minutes. So now we're back from 35 minutes to 40 total minutes. You enter your home street and the truck was even slower than you thought it was going to be. So 40 minutes have elapsed and you're still 3 minutes from home. You can now update them and say, almost there. I know I said I was going to be there now, but 3 more minutes and I'll be home. So you're using what's happening and historically what has happened when you're at that point to generate a prediction that is updating based on that real world information that you're gathering on the fly in the middle of that episode. So that's the difference between Monte Carlo and temporal difference. Monte Carlo would think throughout this entire thing, the estimate for how long it's going to take is 30 minutes. At this point, the estimate for how long it's going to take to get home is -10 minutes. You're not taking into account having been in this state, you're waiting for the trajectory to finish, and then you have one instance of historically it's taken 30 minutes, now I have maybe there are 10 times. It's taken a total of 300 minutes over 10 instances of leaving the office Friday at 6 for an estimate of 30 minutes. But now you do it one more time, we add 43 minutes, so we have 343 minutes over 11 now, giving you an estimate that's more than 30. So you would update that estimate based on this one additional sample at the end. That's the Monte Carlo approach. Temporal difference updates on the fly. Questions on that example or how temporal difference differs from Monte Carlo? You can also visualize it as kind of like this. So we use the actual outcome when we get there to now Monte Carlo would say, how long do we estimate? Do we estimate here? Let's bring this up toward the actual 43 minutes. How long here? We're gonna bring this toward this. How long here? We're gonna bring this toward this. But with temporal difference, we actually find ourselves basing it on how long we thought it was gonna take, how long the estimate is at the next iteration. We're now gonna bring this toward the 40 minutes that was the estimate here. So you can see that this starts to smooth the curve more like the most recent example. It's smoothing the curve rather than pulling the entire curve toward the result. Here, what is the causation for all of this? We don't really know. There's no idea of why did this take longer than we thought it was going to. We just update everything without causation to the result. Whereas here, we try to come up with some causation for it. We overestimated this, but we underestimated this. We overestimated both of these. So it helps to identify the actual causation of something and fail to update something that would become less realistic because there were more factors on your drive home than just how long it took. It was raining, you got behind a truck, the highway was clear, there were more variables at play, and this does a better job of adhering to those multiple constraints. So why does temporal difference work so well? What are the differences? Versus dynamic programming, we still don't need the model that dynamic programming with Bellman required. We don't need the state space. We can still learn from experience like we did with Monte Carlo. However, with Monte Carlo, you can learn during an episode. You're in the middle of an episode, you can learn about what you have experienced so far. Whereas with Monte Carlo, you had to wait until the end of the episode and then backtrack it all the way back to the beginning. You also don't need to ignore episodes that take experimental actions. So let's say, again, you're using off policy Monte Carlo, your behavior policy takes you off on some ridiculous exploratory action that the end result is, of course we lost. It's because the very first move that you made set us up for a mate in 6. Within the first couple moves. So no way were we going to escape from that. So what were you expecting? Behavior policy. So we don't need to ignore episodes with experimental actions because we can look at what were the 2 moves that we did before we put ourselves in that mate in 6 situation. Just like these others, still guarantees convergence, and in general, this will converge faster than Monte Carlo in practice. We look theoretically, we get no theoretical guarantees that this converges faster, but over decades, we have found that temporal difference does in fact terminate faster than Monte Carlo. More of a constant factor, but it's a nice constant factor. Let's take a look at another game. We have 4 minutes for this, so we probably won't get too far. So we start in state C, and we can move either left or right. And the idea is that the episode terminates if we move left far enough to get here, but the reward when we get here is 0. If we start in C and we move right, 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 then we get a reward of 1 when we get to this final state. So we want to be moving right more than left, but it's going to be a little bit more difficult to learn because if we are moving right and left with equal probability, we need to get 3 lefts away from the start or 3 rights away from the start to even terminate the episode. So what does that look like? If we wanted to just initialize all value estimates to some middle ground, like we think that the value being in C is 0.5, the value being in D is 0.5, we will learn eventually from practice that the true state values for this, there are only 5 of them. I don't know why there are 6 of them. This one is invalid. The value being here is 1/6, 2/6, 3/6, 4/6, 5/6, assuming that we have a random policy. But to converge on that, it's gonna take a while to learn. An example of what you might be able to do for this is come up with this game, represent this game in code. And now write an algorithm that is going to try to come up with the values of being in each of these states based on some random policy. So this would be a great way to go practice this. Just note that the actions are right and left. Start with a policy that just randomly does things and see if you can figure out and come up with the approximate value of being in each of these states. You'll find that it converges to those values, but how? Why? What does that say about what we should do in this? Let's say you're in C, which has value 3/6. And you can either choose to move left to a place that has value 2/6 or right to something that has value 4/6. Which one do you do? You move right, because duh. Choose the higher value when you can. But it would take quite a few episodes in order to really get a sense for this to converge, because maybe starting in E, the very first thing you do is go D, C, B, C, D, C, B, C, B, C, B, A, 0. You're gonna have an example of, this was a long episode and it terminated with a reward of 0. Maybe the first thing that A does is B, C, B, C, B, A, B, C, D, E, 1. After just those two trajectories, it would look like being in state A is better than being in state E. But that's just small sample bias because of what happened on that first episode. You need a larger sample size to be able to show that being in state E is better than being in state A. And only through playing this game over and over and over again would you be able to start to see that in practice. How then would you learn? Once you learned the true values of this, you can see that what you're doing again is using that expectation maximization algorithm, where you can now say, once we've learned these values, instead of moving left and right with equal probability, we can now set the policy to be always right. Start in C, there's no reason that B and A should even exist. The only thing you should ever choose to do in C is move right. In D, move right. In E, move right. This game simplifies down to always right, always right, always right. Done. Optimal. But we have to converge to that first. All right, we reached 3:10. I was gonna say that regardless of whether that went off. That was perfect time. So we're gonna stop here and we're gonna take a break for those of you who need to print a cheat sheet or take a breather, go get some water, use the restroom, something to prepare you for an hour-long exam. We'll meet back here at 3:20 to get started.